All right, so now we are going to look at the algebraic way of doing this. So up until now, we've been mainly just looking at the geometric formulas and areas and different things like that. But now we're actually going to get into the algebraic way of finding antiderivatives, looking at indefinite integration. So first of all, let's just kind of think about where we're going here. So if I took the derivative of a function and I ended up getting 2x. So if I have f prime of x is equal to 2x, okay, that we can see right here, what would that original function be? So think about that for a second. What would that original function be? And hopefully you can realize that it's x squared. But the other thing that we need to think about is, will this be the only function that when we take the derivative, we end up with 2x? So let's think about that. Let's look at another one here. If the derivative is cosine, then what was the original function? So that is sine x. And again, think about it. Is that the only function, sine x, that when we take the derivative of it, we end up with cosine x? And one more here. F prime of x is equal to 1 over x squared. So this one's a little bit trickier to think about. But again, if we look at this as polynomial, like f prime of x is equal to x to the negative 2, where did that come from? So maybe we're thinking like 1 over x, but remember when we do this, we end up with a negative sign out front. So we actually need to have a negative here to begin with. Okay, so if we have negative 1 over x, when we take the derivative of that, we will end up with 1 over x squared. All right, now, so let me come back up to my original question here. Are these the unique? Meaning, is there any other function that I can take the derivative of and end up with 2x? And you're probably thinking, well, no, that's, you bring the exponent down, subtract by 1, and you get 2x. But what we have to think about is, what if I add a constant, like plus 5? The derivative of a constant is just 0. So if we look at this, we're not going to recognize that there was a constant there. We won't be able to recognize this. And this is why when we did the derivative graphs back in that motion section, there were different possibilities that when we started out with the derivative graph and we tried to graph the original function, there are multiple ways that we can do that, and this is the reason why. It's because this number outside here, after the x squared function, you could have any constant there, minus 10, plus pi, anything like that. You could have like a minus pi here or something. And when you take the derivative of that, you will end up with cosine of x, regardless of what constant you're adding out here. So that's the part that I wanted you to kind of think about there. And you'll see that show up when we do these antiderivatives. So definition of an antiderivative. If f is capital F is the notation for an antiderivative. Lowercase f of x is how we represent functions. Capital F is how we represent antiderivatives. Of a function f on a given interval I, you could also put like from a closed interval from a to b or whatever in there, so that the derivative of that capital F of x is equal to f of x. Another way of writing this, let me slide that down to give me a little bit of room. Another way of writing this is capital F of x is equal to the integral of f of x dx. Okay, which we know that. You guys saw that. Maybe not with the capital F like this, but we looked at that in previous sections. And like I've been saying, that this symbol is called the integral. So the process of finding antiderivatives is called integration. So we're now just taking all of the derivative stuff and we're working backwards from it. So yeah, let's look at some general forms here, and then we'll go into some basic rules and then some examples. So just a couple different ways of writing this. Like I said, if we take the derivative of that capital F of x, we get to f of x. And that's the same thing here. If I take the derivative of both sides, if I take the derivative over here and I take the derivative over here, what's going to happen is we end up with the derivative d over dx of f of x like we have right here. The derivative and the integral cancel out, so these cancel each other out because they're inverses. It's like taking the square root of x squared. They're inverses, or you're taking e raised to the ln of x or something like that. They're inverses, so they cancel each other out. Oh, it changed colors on me there. All right, so a couple other ways of looking at this. This is what I had written up here. Again, when you take the integral of f of x, lowercase f of x, you get your capital F of x, which is the antiderivative, plus c. This is a very, very important part of this formula that a lot of people miss. A lot of people forget about it. You need to have the plus c there, okay? And what that means is that we're just adding a general constant, okay? Like if we go back to this slide, like I said here, we could add, oops, I was supposed to circle that, not erase it. We could add a constant to any of these functions. You could add any constant. So how do we represent just a general constant? And that's just with the plus c. Now, another thing that I want you to notice is that our integral symbols don't have any numbers. Okay, we're not going from a to b. You'll understand more why later on. But right now, these are called indefinite integrals. When you have the numbers there, those are called definite integrals, as we saw in the notes from previous sections. Those are definite integrals. So now these are called indefinite integrals, which means we're just taking the antiderivative indefinitely. So it's kind of like a formula that will work for any interval, any values from a to b. So we're not making it specific. These are more general. And oops, still have some stuff from when I circled the c there. Let me get rid of that. Basically, if we're taking the derivative, this is like what I said up there. If we take the derivative of an integral, we just end up with the inside. These two are inverses of each other. They undo each other. They're opposites. So, it's just like I had said before, taking ln of e to the x, or sine of sine inverse, or the cube root of x cubed, or something like that. They're inverses, so you just end up with that. All right, so now let's look at some basic antiderivative integration rules. What I would suggest you do here is kind of guess what each of these would be as we go through them, and I'll reveal what they are. So if I take the integral of a constant, c and k are both used to represent constants. If I take the integral of a constant, like the integral of 5, what is that equal to? Well, it's equal to 5x plus c. So to generalize that, a constant times x plus another constant. Okay, and again, this constant out here is separate of this constant. That's why we have to use two different variables. All right, now x to some power of the integral of x raised to some power, where r is going to represent any number. It could be an integer, a fraction, anything like that. Now, if we're doing the opposite of what we had done in derivatives, remember the derivatives, we were taking this exponent, we brought it out front, and then we subtracted by 1. So we're going to do the opposite. Okay, so we're going to add 1 to our exponent, so it'll be r plus 1, and then whatever number we get there, we're going to divide by that number. Okay, so this is what it looks like in your general form. And again, r cannot be equal to -1. You'll see why later. But this is your general formula there. The next one, cosine, we already looked at that one. That is sine x. And then the integral of sine x, you might be thinking, well, it's just cosine. But remember, cosine gives you a negative sine x, so we have to take the negative cosine x plus c. Secant squared, do you remember what derivative gives you secant squared x? Hopefully you remember that is tangent. How about cosecant squared x? Cosecant squared x is cotangent, but again, we got to have that negative there. Secant x tangent x is secant x. And cosecant x cotangent x, again, this is a -1, negative cosecant x. All of them have a plus c because there is no interval on the integral. So I'm trying to make sure I, say the difference in those things. We don't have an a to b on our integral, so there's no interval there. So we need to have that plus c. Okay, let's look at a couple of examples here, and then I will give you some to try and see how you do with them. Turn on this slate here again. Of course, it doesn't want to work now. Okay, let's try again. Okay, so yeah, let's do a couple of examples here. So the integral of x squared dx. Now, what we need to do is, first of all, add 1 to our exponent. So 2 plus 1, and then we will divide by that number, plus some constant that may or may not be there. Your constant could be 0, okay? So it may or may not be there. So we're left with x to the third divided by 3 plus c. Now, how do you check that your work is correct? Well, you just take the derivative of this. Okay, if we take the derivative of this, we have to end up back here at x squared. Okay, so just keep that in mind. You know how to do derivatives, so take the derivative of this. You should end up with the answer up there, but there's your correct answer. Next one, 4x cubed dx. So again, we're going to start with our 4x, raise 1. Oops. I'm already writing the answer down here. We raise this to a power of 1 and then divide by that number. Now you don't really have to do that. You guys can all add 1 in your head. So 4x to the fourth divided by 4, these 4's cancel, and I'm left with x to the fourth plus some constant. Next, 1 over x to the fifth. If it helps, rewrite it as x to the negative fifth. It's not necessary, but it may help you. Add 1, negative 4, divide by that number, negative 4, plus constant. Which again, this you could also rewrite this as 1, bring the negative out front, 4x to the fourth plus c. Okay, that is another option that you can write it like that. It doesn't matter. You're going to be checking your multiple choice answers and see which one's correct. So, square root of x. Square root of x may be helpful to rewrite as x to the 1/2 dx. So, add 1. So 1/2 plus 1 gives me 3/2. Divided by that number, so divided by 3/2 plus a constant. So let's clean this up a little bit. 2x, well, you could write it as 3/2. I'll write it multiple ways here. Over 3 plus c. We could also write this as 2x cubed underneath the square root over 3 plus c. Any of those would be acceptable. You would probably see it. You're not really going to see it written like this, like the first way. It'll most likely be written in one of those two forms, but again, you know how to rewrite those things, so just get some practice rewriting them while you're doing these problems. Now, when we look at this, we're like, oh my word, I have no clue what to do here. So what we need to do is we are going to clean this up a little bit. So first of all, if you recognize something like this that you can't do anything with, we just need to rewrite it a different way. So I'm going to rewrite this. First of all, 1 plus x squared is x squared plus 2x plus 1 divided by x to the 1/2. Now this problem is getting a little bit ahead of myself. This is the last example. It's getting a little bit ahead of myself because this is what we will cover in the 652 notes. But basically, remember, if you have one term on the denominator, we are able to split this up with all of the terms on the numerator. So what I mean is x squared divided by x to the 1/2 plus, let me put a bracket around this, plus 2x over x to the 1/2 plus 1 over x to the 1/2. Okay, so we're able to split that up like that. Now you can't do that if you have x, if this had been like x plus 1 on the denominator, you wouldn't be able to do that, separating them. I mean, you could put them all over x plus 1, but when we have one term on the denominator, it makes it a lot nicer to split it up like this. So let's see what we have now. X squared divided by x to the 1/2. Since these are being divided, we will subtract our exponents. So 2 minus 1/2 is 3/2, so I have x to the 3/2. Plus x minus 1/2 is 1/2, so I'm left with 2x to the 1/2. And then this one, I will just rewrite it up in the numerator as a negative 1/2. Now, remember, limits, derivatives, summation notation, whenever we have them being added or subtracted, we take the derivative, the limit, the integral, we take them all individually. Same process here. So I'm going to add 1 to this and then divide by that number. So add 1, 3/2 plus 1 would be 5/2 over 5/2 plus 2x, add 1 to that is going to be to the 3/2 divided by 3/2 plus x, add 1 to that is going to be 1/2 divided by 1/2 plus c. Now I'm going to leave it in this form. What I want you to do is clean it up, okay? So clean it up and see what you get for your answer, and if you want me to check it or anything like that, just let me know. But just to get some practice with cleaning this up and simplifying some stuff here. This is all algebra, okay? You've done this stuff in Algebra 1, Algebra 2, maybe not with fractional exponents, but you've done it before, so it's nothing new. So just get some practice rewriting that. And here's some problems for you to try. And again, if you have any questions on any of these examples or any of the problems in the book, just let me know, and I will do my best to get back to you.